All right, here's problem 6. It says two girls with masses 50 kilograms and 70 kilograms are at rest on frictionless inline skates. The larger girl pushes the smaller girl, so that the latter, the smaller girl, rolls away at a speed of 10 meters per second. What's the effect that has on the larger girl, and what change of momentum does each girl give to the other, and in what direction? So start with the sketch. So let's see. We have two girls on skates. Okay, let's see here. Inline skates, right? They're going to kind of push off on each other, yeah. Right, and then the smaller girl. I need this marker's not so hot. Let's see here. Smaller girl. Just kind of push off like that, right? Okay. So let's see here. We know. He told us. Mass here, 70 kilograms. Mass, 50 kilograms. That's the before picture. The after picture. So they're starting at rest. Okay, so that initial velocity is 0 for both of them. Afterwards, they're going to push off. And we know the smaller girl, right, is going to end up rolling backwards, right? Right? At 10 meters per second. That's quite a shove, right? And so you say, well, recognizing this and saying, hey, if I look at this whole system, you say, there's no outside force on the combined large girl, small girl system, left and right. There's no outside force. Left and right. So the left and right momentum has to stay the same. We start with a momentum of 0. The total at the end's got to be 0. She's going right. We got to have some momentum left to balance it out. So that big girl, we know the larger girl, is going to end up moving backwards. So she's going to roll back the other way, right? So what I would say for part A is I know that if the little girl gains momentum one direction, let's call that a positive direction, okay? Make that a positive 10 meters per second. Let's call it right positive. Then larger girl's got to gain momentum in the negative direction too, okay? Let's just write down larger girl and smaller girl. There we go, LMS. Yeah, that's what they were described. Yep. Okay, good enough. So what I know is got to happen. What is the effect of the action on the larger girl is to cause her to roll backwards. Gaining momentum in the direction opposite to the smaller girl. Okay, there we go. Okay, part B. Part B asks, what change in momentum does each girl give each other and in what direction? So really, let's just find the change in momentum for each one. Part B, we want to know, okay, what's the change in momentum of the large girl and the change in momentum of the smaller girl? Okay, is what they're really asking us for. Well, I don't know this velocity the larger girl has, but I do know the starting and ending velocities for the smaller girl and over mass. Let's just calculate the change in momentum for the smaller girl. In fact, what's going to happen here, if I look at the whole system, which is kind of the way I was thinking about it as I was figuring this out, looking at the whole system, right, a combined system, larger girl, smaller girl, if I do my F delta T is delta P for a system of the larger girl and the smaller girl, yeah, then I'm going to have no outside horizontal impulse. Okay, I'm assuming these inline skates are essentially frictionless, right? Really low friction, so we can friction's negligible. small enough we can neglect it, then I'm not going to have any outside horizontal force. Yeah, gravity will pull down and the street will push up, right? But those forces are balanced out anyway, so total force is 0. But most importantly, they're not pushing sideways, so they don't affect the sideways momentum. Again, momentum has a direction, and we can talk about it in the x-axis or the y-axis. Our horizontal axis, we've got no momentum change, right? Overall. However, this delta P, we can expand that out now to be change in momentum for the larger girl and the change in momentum for the smaller girl. You say, look, they've got to add to 0. They must be equal and opposite. And that's why we were able to say, hey, the larger girl gains momentum opposite to the smaller. Make sense? Two things adding to 0, got to be equal and opposite. Okay, now, can we calculate these? We don't know the values for delta P larger girl. We don't know her velocity yet. We do know enough information for the smaller girl. And because these will be equal and opposite, we'll have them both. So let's just solve for that. Delta P smaller girl. You see, well, that's just going to be momentum of the smaller girl at the end minus momentum of the smaller girl at the start, right? Final minus initial. You say, hey, wait a minute. The initial momentum was 0. So that term drops out. So now I just want to find that momentum of the smaller girl at the end. That'll just be using the formula T equals mv, mass of the smaller girl, velocity of the smaller girl at the end. And you say, hey, that's just going to be 50 going at 10 meters per second. You say 50 times 10, that's 500 kilogram meters per second. That's the change in momentum for the smaller girl. You notice that I chose to call right positive, and so she's gaining momentum to the right. That's her change. You see, with these changes, they're equal and opposite. So if I put 500 in here, delta PL plus 500 is 0. Delta PL had better be negative 500 kilogram meters per second. Now, when you set up this problem, it is possible that you might have drawn it like backwards from me or assigned your axes backwards from me. You might have made this a negative 10, meters per second. And then just your signs would be flip-flopped. But you should still get 500 kilogram meters per second. And that is problem 6.